We've looked at all the different types of improper integrals, and so far all the examples have been convergent. I want to talk a little bit about divergent improper integrals for a moment. So, we already looked at this integral from 1 to infinity of 1 over x squared dx. And if you recall, when we were finished, we saw that that converged to 1. In other words, when you're looking at the picture, as you go farther and farther out there, the integral is getting closer and closer to 1. Now, this may lead you to think that, oh, okay, I see. What causes this to converge is that the function is getting closer and closer to the x-axis, so that area is getting tinier and tinier. Well, that's only half the story. It not only has to come down to the x-axis, it has to come down to the x-axis fast enough. Just going down to the x-axis or having an asymptote of the x-axis is not enough. To contrast that, we can look at something very similar. Say the integral from 1 to infinity of just 1 over x dx. All right, if we look at the graph, it doesn't really look all that much different, right? It starts at the same height, and they both start at, when x is 1, that's 1. When x is 1, that's 1, and they both go down. It's just this one goes down a little bit slower than that one does. So what happens as we evaluate that? So again, remember, first thing we do is make it proper. And the first thing you're going to notice is that this integral is just categorically different, right? This was power rule. This is no longer power rule, right? This is the derivative of natural log right there. So we're looking at the limit as b goes to infinity of natural log of b minus natural log of 1. And remember my example of Alpha Centauri. Natural log of b there, that's growing very, very, very slow, but it does grow without bounds. So that's infinity. This is just 0. So that's infinity. So even though this function's getting closer and closer to 0, as you add up, so what did we see here? Before we evaluated the limit, if you stop here at b, what you have underneath the curve there is natural log of b minus 0. And so that accumulation, as you slide farther and farther out, just keeps growing and growing and growing without bound. Whereas over here, we saw as you come out further and further, you grow and grow and grow, but you're growing up to and converging to 1. So it's not enough just to come down to the x-axis. You got to come down quick enough. And as it turns out, this is the boundary case. Anything that comes down faster than 1 over x is actually going to converge. Anything that comes down to the x-axis any slower than 1 over x is going to diverge. We're going to look at that in further detail later on. So it's not enough for this function to head to 0. It has to head to 0 fast enough. Now the other thing I wanted to look at with divergent integrals was we looked at that interval from negative infinity to infinity. And I just want to look at something to make sure we understand the definitions. Let's look at this example, the integral from negative infinity to infinity of x dx. Now, a common misconception might be to say, well, if I look at that graphically, here's my function, right? This is y equal x. Well, there's a symmetry here, right? So, if I stop anywhere along here and go from some negative a to a, that negative bit will cancel that positive bit, and it's 0. So if I just keep going out, it's just more 0, 0, 0, 0, 0 the farther I stretch out in either direction. So you might think, well, this chunk cancels that chunk. There's nothing. It's 0. The problem with that logic is what you're doing here is not what we defined that to mean. We didn't define that to mean the limit as you took both the lower and upper limits out at the same time. We defined it to mean the limit as a approaches negative infinity of a, say, up to 0 of x, and then add to that the limit as b goes to positive infinity from 0 up to b of x. And recall, now when you do this integral, as you were just probably thinking, okay, this is divergent, right? As I go farther, it's clearly divergent, right? As you go farther and farther out this way, that triangle is just growing and growing and growing without bound. So this limit, when you evaluate it, is negative infinity. This limit, when you evaluate it, is positive infinity. And those infinities don't cancel. As I mentioned before, that's divergent. So this think of that as does not exist. So you can't take something that does not exist and add it to something else that does not exist to get something that exists. So this sum, this is divergent. So don't think of those as canceling off. So it's, like I mentioned before, as soon as one of these integrals doesn't exist, the whole thing doesn't exist. So remember, we have to go by what we defined that to mean, and we defined it to mean those integrals right there.